Today we're going to talk about multimedia sciences orders of magnitude and scale materials. This is a set of materials that is a website-based set of information that talks about the orders of magnitude and scale. And then there is a piece of software called the orders of magnitude application for students to run an experiment to illustrate the idea of scale. And the end result of the discussion, after we go through the metric system, a review of the metric system, how to run experiments, getting a feel for what the idea of scale is the fact that many equations, many physical processes change with scale. So that if you increase the length of a spring, you just can't do that indefinitely. At some point, the spring constant, the equation of Hooke's law, fails, and when spring gets so long, it breaks. And this happens sometimes less dramatically, so that it's hard to know that a change has occurred. And that leads us to the main experiment, which is the styrofoam balls experiment, which has students throw a number of styrofoam balls after they've made a hypothesis on which balls will go further. And what happens is they get the exact opposite results of what they would think, because the density of the balls has changed in scale. So it's a very interesting set of materials that has students have to do some fairly heavy thinking, and the styrofoam balls experiment is fairly complex, but lots of fun to run. So let's just take a look at some of the pieces of the orders of magnitude and scale materials. And so first of all, there is an overview with links, so you can see that what I've talked about here is all listed. Let's just quickly take a look at the idea of an order of magnitude. It shows that we can go from 10 to the minus 18th, that's quark, all the way up to 10 to the 26, which is the size of the universe. So an order of magnitude is increasing the size or decreasing the size by a factor of 10. There are links to various websites that you can use as part of the presentation. We talk about the metric system with some questions. For instance, which countries do not officially use the metric system? And the answer is not many. Basically, the United States and Burma. We're in proud company here. We talk about metric prefixes, running experiments, talking about confounding and dependent and independent variables. We have some worksheets where the students will get a feeling for scale, the width of a human hair, the diameter of a molecule, and so on, and see whether they can place these objects in the correct scale. Then we start to talk about how things change with scale, what you can see depending on scale, how models change, how the effects of forces change with the size of the variable or the size of the object. There's a brief history of nanotechnology, certainly an up-and-coming field. There's a crossword puzzle that you can download and an answer key. And then there's an order of magnitude application. And this has pictures that we're taking with the SEM microscope from Drexel University. The pictures were made by the scanning electron microscope of zinc oxide, and they're called nanowires that we use to make a solar collector. So there's a lab handout that goes along with that, and then there's the application itself. One is to look at a flashlight filament. So you can see it not too easy to measure with the ruler here when we're at a decimeter range, but as we increase the size, you can see we can get and start to measure the size of that filament. You notice that as we go up and down, the ruler changes as far as the prefix of the metric system. You can see some pretty pictures here of the filament of a light bulb. And unfortunately, once we get to a certain point, there's nothing to measure at this point. You can also add some horizontal lines to help in the measurement, drag them to where you want so you can get an accurate idea of the measurement with the ruler. The next one is the nanowires. So again, not all of these orders of scale can you see anything, but here is our first chance to start to see at the millimeter range the nanowire, and as we increase it, we can almost start to see it now. And when we get to the micrometer stage, now we can really accurately measure the size. There are, of course, directions for the students to help them figure out how to take the data. Let's take a quick look at the handout. So here's the order of magnitudes handout that you use with the orders of magnitude simulation. It's going to ask the students to take measurements at various scales and ask them a number of questions based on their readings, the last of which is if the area covered by the zinc oxide crystal was made up of nanotubes similar to the one measured above, calculate the number of nanotubes that would be there. It's actually a fairly interesting calculation. The other thread that runs through the handout is the idea of significant digits, and depending on the size of the ruler, whether or not they're, what kind of percent error are they getting based on the fact that the significant digits change. So the experiment is the effects of scale, the styrofoam ball toss. You'll need a set of styrofoam balls, which is pretty easy to get at any local accessory shop. And the students will throw the styrofoam balls. They try to do it with the same force every time, which is pretty much as hard as they can. The balls will not necessarily go in a straight line. I worked on this with a couple other people when we developed it, and we thought, well, there's no way that this experiment is going to work with balls, moving the way they were, and the difficulty in getting them, not to fly upward or downward. To our surprise, the results come out really, really great, and the students really have a good time with this. So you can see there's a bunch of descriptions on how to run the lab. They take some data, and we ask for the diameter, the mass, the distance that the ball goes, the surface area, the volume, and then the m over the mass over the surface area. And they're asked to come up with a hypothesis, again, of what's going to happen. And most students think that the greater the mass, the shorter the distance that the ball will go. You can see that we make some graphs: distance versus mass, distance versus surface area, distance versus volume, distance versus mass. And this turns out that this is the one that works because the surface area, the density essentially, is what determines how far the ball goes. The scale determines exactly what kind of relationship you're going to get. There is an Excel spreadsheet that has a set of sample data and all of the graphs. It's up to you whether or not you have the students do the graphs by hand or whether you have them do them in Excel. But at least this is a nice answer key that you have available for demonstration purposes. So this is an overview of the orders of magnitude and scale set of materials for multimedia science. I find that the students really enjoy. There's a lot of real life examples here. The lab is a lot of fun. Does a great job of reviewing the metric system, metric prefixes, and how to run an experiment. And it's a fairly complicated experiment to analyze a lot of graphing. So I enjoy this set of materials a lot. So if you're interested in finding out more about the orders of magnitude materials, please check with Teachers Pay Teachers at this URL. Multimedia Science makes a bevy of simulations, games, challenges, experiments for chemistry and physics. It also carries a number of game-making tools that you may find useful for games of your own, review games of your own for your students.